Good morning. Welcome to episode number 41. I hope I got it straight this time. As you can see, things are a little different behind me. Let me scooch over here. I got a tripod over here on top of ZOOMTOWN with a camera over this end of it, which means we're starting the transition over to ZOOMTOWN for all the rest of the experimenting and testing. I got a Zoomie set up down there. It's still running on an umbilical cord because the code is still being developed, etc. I've got 8 driveways here all set up for us to finish up all the code development. I've got the markings on the roadway, which you kind of see right here. And in the overhead you can see it very clearly. We've got the markings. I've got the magnets embedded in there for the start location of the various inch markers when we back out of a driveway, etc. So all around, this is kind of the final phase of testing and development before we start going, we'll call it full scale, and start moving around the whole layout. Also in the background over there, you can see the scheduler software. I don't really want to go into a lot of detail on that. I kind of want that to be a side aspect of the whole ZOOMTOWN experiment, but I'll explore it as you guys you lead me what you want to know about it. But that's in development right now and has been for a very long time. So this episode is going to be about getting our turns straightened out. My original plan for turning was to use the encoders only to do the steering of the Zoomie. I discovered along the way that that was not going to be anywhere near precise enough with the type of encoders, the hardware, the mechanics of what I've got to work with. So I had to change from my original plan, and that is to use line following through our sweeping turns. And on the overhead up here, let's see, try to get, well actually it's probably easier here. These would be considered sweeping turns, here and here. And then everything else would be right angle turns. And that's what we're going to talk about specifically today. The coding of that, and then a demonstration of how well or how bad it's working. So let's get into the details of how I'm going to cover all this. We'll start out, a pivot turn is a turn made by rotating one wheel while the other wheel remains stationary. In other words, it's going to pivot on one wheel. The features that are presented with that, it requires a minimal amount of space to perform. It can turn very sharply. It requires the least amount of control to perform. The program logic is brilliantly super simple. It provides improved positional accuracy, improving localization, and that's because of its sheer simplicity. Only one motor, one encoder has to do anything during that motion. And it can be performed in forward or reverse, unlike line following around a curve. The applications I'll be using, pivot turns, will be turning into a driveway, turning to align with the road when backing out of a driveway, and all controlled road intersections that intersect at 90 degrees. And that would be everything that isn't a sweeping turn, such as this. Those aren't covered under pivot turns. But every other intersection on the layout, such as here, here, over there, those are all controlled intersections, meaning it is intended for the Zoomie to stop at those locations. So we pull up to its stop just like you would in most city streets driving a real car. Now let's take a look at how we'll be covering the Sweeping turns. A sweeping turn is a turn made by rotating the two drive wheels, but at different speeds. The feature of it is they look much more graceful and less robotic. I myself, personally, I don't mind robotic moves with a robot, but I needed to expand a little bit on that. And it also can use, the sweeping turns can also use line following for steering. And that's where it was just a matter of adding in the guideline that was absent with my original plan. There are issues with it, though. It requires a lot of control to perform. Not necessarily bad or anything. We're going to have to perform steering and guiding, and frankly, our line following really kind of handles all of that. There is another issue with it. XY positional tracking is more complex, and what I mean by that is, on a pivot turn, hopefully we can see this, the Zoomie would come up to a location. It will pivot on one wheel, line up with the line going that way, and continue on. So during that motion, realistically, I would show the Zoomie while I'm tracking it with the scheduler over there. I would show it in this position, and theoretically I would show it in this position before it moved. And that would work perfectly fine for our tracking and everything. We don't really need to do too much concern. Once I get clearance from the scheduler to make the turn, I'm not really concerned about showing the about 25 to 35 millimeters of movement in between there. Now when we get over to the sweep turns, and I'll drive backwards on this so we can see it a little bit better. As we're going along this way, this is what I'm talking about. It's very hard to mathematically, especially with the Zoomie, to calculate exactly where the Zoomie is in X and Y coordinates, because in the line following routine it actually thinks it's going in a straight line. So there isn't knowledge of the angle related to the center as to where the Zoomie is. So that's going to be possibly a problem. I really don't know. If it is, I'll have to add in some logic to figure that out during the turn. The reason why I say that it probably isn't a problem, we don't need too much guidance from the scheduler during this movement. So it's not necessarily a problem that I can foresee yet. Another issue with the sweeping turn, because it's using line following, it can only be performed in a forward direction. You cannot do line following going backwards with this mechanical layout on the Zoomies that I've got. And finally, the applications for the sweeping turn are strictly are restricted to simply the sweeping turns. We don't need pivot turning out on the bypass, as I'm calling it. Think of that as the outer bypass of a city or a town. And I don't need to do pivot turns there, so the only application for the sweeping turn is on the outer bypass, and it would not be done or performed within the, we'll call it the city limits. Now in this video I will be providing source code, and I'm going to give you a forewarning right now. The program is very much in a transitional phase from what we've been doing and how things are being done now. It's going to take a little bit further along before I want to explain the program as a whole and how it operates now. So please forgive me for my brevity on any explanation of, wow, that's all different. Let's focus on the task we're performing, and then in about 2 or 3 more episodes, hopefully I can bring everything together as to how everything changed, how it will operate, and how I integrate it with the scheduler. So we'll go through this code here in a minute, but the first thing I think probably would be best is a demonstration of our pivot turning as I go around a little bit of the ZOOMTOWN layout. not so bad. I think that's a really good demonstration of how well we're doing with localization and positional tracking, as well as the ability to precisely make the pivot turn at 90 degrees and where we want it. So all around, the performance is looking really good. In that demonstration, you've seen just the left-hand turns. We'll go over the code a little bit, and then we'll come back and do the right-hand turns, and then we'll talk a little bit more about the code. Here's the program. I'll probably be packaging up 2 in this, and I'll explain that, why that'll be. Let me get all the way down to the bottom here first. And it's getting to be a rather long program because of the new way I'm trying to handle all the motions. This particular code here, you'll see it, I call it my trip plan. This is currently how the data would have come from the scheduler, or is right now theoretically. And each one of these, it's 3 lines in a list, and that each one will describe how a motion is to occur. For our example right now, we're looking at PTL, pivot turn left. I don't need to give it any distance, and I don't need to give it any preset positional data. It's strictly a canned routine because no matter which way, well, no matter where the pivot turn is on the layout, it moves the one wheel exactly the same amount. The position up to that is the critical part. So programming that is the easy part. And want to get down a little bit further here. Okay, and there is here an interesting thing. You'll see a PTL, pivot turn left, no positional data, and then a PTL with the positional data set to 0, but the third parameter set to REV, reverse. So it's the same routine, functionally the same routine, it's just one is performed forward, the other is performed reverse. Now this is how the Zoomie will be told to make the move that isn't performing anything yet. Let me scroll up. This is pivot turn right here, pivot turn left. We're going to do a little bit of variable setting in here, and this is all subject to change as well. The travel distance is based on the wheel spacing times 2 times math.pi divided by 4. In other words, a quarter of a circle relative to the spacing between center line of the Zoomie and the center line of the tire. That is the radius we're actually moving. All right, now we need to set whether it's going forward or reverse. That's critical. In this case, we were told that. It was passed in on our second parameter. We set our velocity parameters, tell it the Zoomie routine that it's in a motion algorithm, and then I print out the data. And then that starts the motion. It prepares all the data for the motion and gets it going. Coming up higher in the code, there's a pivot turn right, pivot turn left. We're just accessing a lot of global variables, and a lot of these variables are mostly related to position tracking, because I'm right now, currently, at what you will see, we're actually only tracking, so to speak, positional data along the length of our line that we're moving, or the length of the road we're moving. Eventually, I got to also keep track of the X and Y global absolute position of the Zoomie. And all that kind of feeds one another, so that's why they're global variables and they're accessed everywhere and can be rewritten in other places within the program as a whole. But that's pretty much the startup of the code. Here we are, left incremental distance, right incremental distance, or inch distance to go. We calculate that just so it knows how far to go. And then it keeps moving until our inch distance to go is less than 0.02 inches or half a millimeter, and we're making a pivot turn in the left direction. Once we achieve that, we'll stop the motion. That's it. Pivot turn right at the moment is basically the same. It has not yet been enhanced for the forward and reverse coding. So that is the routine. Now down in the main loop, just like the other motions, depending on which motion is running, in our case pivot turn left, it will call that function to perform the pivot turn for right or left, depending on which one, as you can see here. And that's structurally very different than what I originally intended how this program would work. But so far it's been working very well. Now let's take a look all the way back down into the code where we program the motions. And right here, if you remember, the Zoomie started way over there, where it is right now, and that's at the start of a sweeping turn. So the current naming for that is FLM, and that means forward line steering to a marker. And that actually just got modified, and I'm still tweaking its functionality, so I expect that to change ever so slightly. But I must specify a distance for it to go, and that distance would stop just a little bit short of the starting point for the following line. Now let's take a look at FLM in code. Here is the function for line follow to a marker, and that gets us around that sweeping curve. A lot of global variables. We handle our steering adjustment for line following in this code, just as we did with our regular line following. Over here, we're looking for a marker transitioning to off and a position being greater than 1 inch. And all that's really doing is, well, let's go backwards around the track. I want to make sure, see this piece of tape here? Oh, you can't see it. Again, camera angle. This piece of tape, the Zoomie could be on that with the sensors. And we don't want it to react to that marker. So we're just going to say, you have to move at least 1 inch before I start looking for the end of the motion, or until I get to the 10 inches of travel we specified in parameter 1. And that's what this is about here. So it's making that determination. Are we clear of the very first marker, which could be a remnant from the last line we were on? And then we'll update our position data. In this area, that will in turn update all this positional data, allow us to update it. And then we're going to check and handle for deceleration, just as we did with line following. And what that routine does is it looks at the type of motion, the current position, and how much further it has to go, and then it'll decel to a stop if it's within a specific range. So that one kind of does a lot of work for us. Down in the main code, you will see this was FLM, and that is right here. If motion equals FLM, line follow to marker. And that's how it's getting through the sweeping turn. Now, there is a little quirky behavior in there, and I'm still experimenting with that a little bit. So this might get changed slightly over time here, but what I have to do now that I'm over here on the ZOOMTOWN layout, the behaviors I expected to be different because the TCRT 5000 isn't a color sensor. It's detecting, we'll call it a grayscale for the lack of a better way of putting it, how much reflective light's coming back from the surface. If you remember, ZOOMTOWN Test Track Z was black. This is a dark gray. in this area, so the color contrasts are different, and I am experiencing slightly different behaviors, so I've got to work with it a little bit, make sure I understand that behavior, and then make slight adjustments. Hopefully that all makes sense. And hopefully I won't have to go into a huge long dissertation on all these little differences. I'd rather get them cleaned up and not have to worry about it. So now what we'll do, we'll just take a shorter trip on it, showing right pivot turns. And then from there, I think we can wrap up this video, and I'll give you a little hint as to what's coming up in the next video. Looking at the code for this one, this is Z-30-16-E41-R. It actually makes sense to me. Not a lot different in all of this. The PTLs are now PTRs, and we got to specify forward, reverse, etc. The FLM is the same. The value is different. It's a smaller radius. And as you will see way over here, instead of going all the way around this way, we're only going around this way and stopping right there. So that isn't much different. And then from there, it's just kind of repeating it. We're pulling up to each driveway. That's what these are. We're going to forward lines follow steering, stopping at 1.875, 7.775, and each of those are the inch positions for each driveway. So let's see if she'll make that run. We'll do in the right pivot turn. So far, this testing with the pivot turns, the sweep turn, the line following, our inch markers, the magnetic markers, all of that is working, dare I say, very reliably. I'm really happy with it. Now next up, I got to get the Zoomies in and out of the driveways. Every trip starts in a driveway and ends in a driveway. So I've got to come up with a maneuver to get from the road into the driveway, and then from the driveway back out to the road in the correct lane and in the correct heading. So that'll be the subject of next week's episode. And I think with that, we'll wrap this video up and save some good old fun with numbers and programming till next week. Thanks again for watching, and I look forward to seeing you then.